talk about Potts model, ON nonlinear sigma models, and spanning forest, and I think many other things too.
Well, yes, not many. Well, it depends from time, of course. But luckily, I've been not one of the first one to speak in this workshop. Instead, I've been preceded by many people who introduced many useful concepts. So I thank all the previous speakers for having done that. And I'm afraid that I will not be as useful as them. Also, I will not give you a complete historical perspective on this framework, variegate framework of generalization, different generalization of matrix T theorem, and different kinds of summation over forest, which we have seen around in this conference. I will focus on my own small work in a sense, and I apologize with all the other authors which have done interesting things on these fields, and most of them have either already talked here or will do that. So sorry if I do not make many citations during the talk, but I will try to do that. Well, a few of people I will do that. So I see that here a large fraction of the people comes from a mathematical background, so I wanted to give you an introduction from a statistical mechanics point of view. I'll say something at the beginning. Well, I was going to make a talk with slides, PowerPoint slides, well, LaTeX slides. But at some point, I showed them to Alan Sokal in order to ask him some small advice here and there for citation and so on. It destroyed the whole presentation, so I'm going to do that at the Blackboard now.
I said you subjected to a permutation.
Yes, but, well, I hope that at the Blackboard it will be nice. So if you have, okay, if you have complaints from the way I'm writing and so on, just tell me if you are on the back and so on.
It's all out on Spalt anyway.
Sorry?
It's all out on Spalt anyway.
Right.
Okay.
Maybe we should
Wait.
Oh, you're going to use this?
No, but the man explained me how to do that. So I will start talking about these two models that we want to prove they are in correspondence. There are two models in statistical mechanics. One of them is the Potts model, Q-color Potts model. It's a model in statistical mechanics, and it's a quite natural generalization of Ising model, the famous Ising model that Kotetsky also talked about. And in the sense that in Ising you have variables that you can think they are +1 or -1, but actually the interaction is such that you can just think that they are white or black bullets. And you are putting a price if the two bullets have the same color. And in case if you have a magnetic field, a price if they are of a given color. But we put the magnetic field to 0 for a moment. And so why not using bullets of Q color instead of 2? So we will have a kind of we have the Gibbs weight. We want to calculate partition function, so we introduce a measure, a Gibbs weight, and we sum over that. So the Gibbs weight is, in our case, some product over the edges of a graph, the graph which is describing the pattern of interaction, something like this, where these sigma are the variables I'm working with. They are leaving some space 0, 1, q minus 1. But you see there is only a delta, not quite a general kind of interaction. This is somehow telling you that I'm not using these labelings as numbers actually as they were having a mathematical structure. I don't do 1 plus 3, for example, something like that. They could have been colored as well red, blue, green. That's the reason why I also make a picture in colors. There is no special structure. Yellow and red, they are not consecutive along in a cyclic order somehow, in any way. This is an important fact, because as you will see in a moment, we are talking about the number of colors, but we don't want to study q equal 2, 3, 4 separately. We want to understand Q color Potts model somehow, analytically in Q. And analytic continuation is an issue which will be trivial. Well, not totally trivial, but easy for this kind of interaction. While it is in general much harder, there are interesting papers, but people, I can tell you citations, but I promise not to do that. So we have just a symmetry which is a global symmetry under relabeling of these names, which is thus a permutation symmetry. I will say the word symmetry many times in this talk, although this is a trivial symmetry. I want to stress it because other symmetries will be less trivial. In particular, as we start now with the ON nonlinear sigma model. This is a different model. This is a model of unit vectors in some space. We have variables sigma with an r of I in some r to the n, but they are somehow constrained to be of unimodular. There will be some quadratic form. Why go complicated? Just take the ordinary quadratic form. So alpha is going from 1 to n is again an integer. You cannot work with arbitrary n. Again, when n is equal to 1, we have our kind of Ising model, because unimodular on a line is just plus minus 1. Well, I didn't tell you which is the Gibbs weight. The Gibbs weight is, well, let's forget that this constraint is already there in the integration measure. If you integrate on r to the n products over the vertices, you have to implement the constraint with a delta factor. So it is here. Sorry, it's a bit small. So we have the delta implemented here, and the small factor 2 because this is quadratic. It's natural to do that. And then we have an interaction which is just putting a good weight if the sigmas are aligned in a sense. So why here we were having kind of a order-disorder transition in which if you take J strong, you give a good price for sigma having a good the same color. So although you lose in entropy, you gain in energy, and you can have the space transition with this Ising-like mechanism. You have a similar mechanism here in which you tend to have alignment because you gain energy, and disalignment because you gain entropy. But of course, sigma now are continuous variables. This is important for many purposes because you can have Gaussian mode, different mechanisms which are not present, or maybe present but hidden in post-model partition functions. And again, we want to understand an analytic continuation in n, but we will see that this is a harder issue. OK, there are other choices that you can make here. This looks just the most natural. You take the scalar product. Why not? But there is a variant that is more nice for what I'm going to do, which is what I call RP, unfortunately, n-1 model. This is the variant of variables constrained on S n-1, the sphere, in n dimensions. We take the quotient with respect to a plus-minus sign. This means that the Hamiltonian is equal to the Hamiltonian gauged by some epsilon. I mean here that sigma I going to epsilon I, sigma I, epsilon I equals plus minus 1 is a symmetry of the theory. For course, it is a symmetry of the integration measure, so it's sufficient that it is a symmetry of the factors here. So maybe the good factor is the one in which you have wij, sigma I dot sigma j squared minus 1 over 2. That's better if you take over 2. Again, there is a subtraction in order to take zero energy if you have the totally aligned case. And So this is called local Z2 symmetry. In addition to the, of course, ON global symmetry. By which I say that the action is invariant if you rotate all the sigmas with the same rotation. This is the justification for the name, of course, ON. And the name nonlinear comes from the fact that if you prefer thinking in n-1 dimension because you are locally near to a sphere, well, then soon, if you stay not so locally, sooner or later you feel the curvature of this sphere, which is called a nonlinearity in a sense. So this is the name of the game. Well, I justified you that I'm interested in analytic continuation, and I start with Potts model, which is easy. This dates back to Fortuny and Castellan in the 70s, but maybe also before. And as you will see, we will recognize a structure which is dating back to the 50s to that. So I do that in some details, although it is easy, because it's some mechanism that I use again and again. The idea is that those factors e to the j delta, as delta is valued 0 or 1, you can write them as 1 plus v delta. Just take v equal to e to the j minus 1. Quite similar to what happened in Kotechi talk on high temperature expansion, where this term here was valued plus minus 1, so you can, of course, match it the function. If you do that everywhere, you see that in that product you have a product over edges in J, 1 plus v ij delta sigma I sigma j. Every time, trivial lemma, every time you have product over ij in some graph, 1 plus something of I and j, and then you sum over some sigma, you can understand this as subgraphs somehow decorated. Because when you take 1, you have a trivial factor, so it's advised to take kind of saying this edge is not marked. If you take the rest, sooner or later something will happen. So it's like to say this edge is marked. So you can write it as sum over spanning subgraphs in G, product over ij in h of g in e of h of phi ij, and of course these are the only ones depending on sigma. And so the sum over sigma commutes with this sum.
Why do they have to be spanning?
This is a good terminology, because somehow people typically say that a subgraph of a graph, if G is a graph defined by V and E, people say that H is a subgraph of G if H is some V prime E prime, in which this is a subset of this is a subset of this, and they are compatible. It is spanning if V prime is just V. You don't care about V prime. If it is so large, E prime is automatically compatible. It is sufficient that it is a subset. And so this is why the possible E prime are just the trivial set of, they are, of course, in isomorphism with 0, 1 to the n, where n is the number of edges. You can, every edge you can take it or not. So that's why they are in bijection with this trivial product of binomials.
Sometimes you can also say that it's some overall subset of edges.
Yes, at some intermediate state, I would have written sum over E prime subset of V, sum over sigma product over Ej in E prime of phi.
Right. So the confusion, I guess, for some non-combinatorialists, spanning just means all the vertices are there. It doesn't mean they have to be touched by edges. What?
That's a confusion for combinatorial.
Also, okay, so possible confusion for everybody. Spanning just means all the vertices are there.
You can have isolated head.
I can have isolated vertices
You can
and
forget about them and have a subgraph.
But
But you
no,
can't forget about
Just
the
don't do
exceptions.
that. Just another, the better way to think about it is just, it's a subset of the edge set.
exactly.
Vertex set never changes, it's always B.
As I know that this leads typically to confusion, when I draw my own spanning forest here, I deliberately choose two of the components to be isolated vertices. And every vertex is marked in blue. Every vertex is there. So, well, you will say, why do you use the letter H as it were a subgraph instead of using just E prime? Well, that's because when you sum over sigma, you produce something with this phi, which typically depends on the subgraph in some topological way, which is not easily encoded in E prime, but it is easily encoded in H. For example, in pods, you will see that this will count connected components. How can you read connected components on E prime unless you draw H corresponding to E prime? And so in particular, yes?
So eventually the phi ij will depend on H, not just on sigma I and sigma j?
Well, the phi we are summing over. This one will produce some single factor tau of H, which is the result of this integration in a sense.
I don't, above there, the first line on the board,
Yes.
right, is summation over sigma over all the edges 1 plus phi, right? And then if you interchange the summation and the selection of edges, the selection of the 1 and the phi, you get a summation over subsets of edges, and then summing over sigmas. Okay, so is the lowercase phi the same as uppercase phi there?
I've been lazy here, yes, because it was asking me more short.
Okay.
Sorry.
And then, but up there, the top line phi is not a function of a subgraph.
No, well, I assume that it's the function only on sigma I and sigma j.
I see. So there the product is over the edge set of H. So that's how the dependency.
Yes,
Okay, got it. Okay.
But you see, interchanging sums is, in general, dangerous if you are sloppy and you want to describe things in the continuum limit or in the infinite volume limit, and you use it in some structural way because you use translation invariance and so on. You never know what happens here. I will do everything today on arbitrary finite graph, at most arbitrary finite hypergraph. So although typically I am the kind of speaker which would tend to make these dangerous things, this does not happen today. So
Today you're not being a physicist, you're being a mathematician.
well, maybe not none of the two, but for sure not fully a physicist. So, well, we are here. So we use this small lemma, so we can write this partition function of Potts model, z of Potts, we can say, as a sum of a subset of G of the sum of a sigma. Oh, well, we have two factors. I split them immediately because that's instructive. This is the trivial part. You just take factors which are numbers, so you dig them away. Then you have sum of a sigma of the same product, which now has the bunch of deltas. This is in principle, with the general lemma, something ugly. In this case, it's so easy. It's just telling you that H has some components. Each component is such that you have a bunch of deltas which are connecting all the spins in the component. Every two spins are connected by a path of deltas. They have the same color. except for these, all the components are uncorrelated. There is no interaction between them. So each component in the summation gets a factor q and nothing else. So this boils down to just q to something that I call k of h, just the number of connected components of h. I'm using my letter k of thought in the seminar of Olivier. It was called C, but I hope this doesn't make confusion. So this is what you have now. Z of course is just sum of a subset q to the k product of the w's. If it were not for the q, it would have been a trivial partition function, products of 1 plus v. So for q equal 1, you get the trivial partition function, which is the one of the so-called model of percolation. In general, it is hard. Well, for q equal 2, you get Ising, which is interesting on its own, and so on and so forth. But you see, this is a polynomial in q. We have a finite graph. The highest degree it could have is the one corresponding to all isolated vertices, which is q to the number of vertices of G. This is perfectly well defined. This is polynomial, so we have analytic continuation in q, just studying this polynomial as a function in Z, in C. This expression, the people will know that we realize that it's essentially the dot polynomial. Actually, yes, we have all these v which are different. It's the multivariate dot polynomial. Actually, in order to recognize the dot polynomial, you should make some change of variables or things like that. But I do that not only for connecting to dot polynomial, but also because I like it more. So let me define something that I call Z of random cluster partition function of a graph G, a set W of edge weights, say symmetric, and two parameters lambda and rho as the sum over subgraphs of lambda to the number of components in H minus the number of components in G itself, because why not? This will be integer anyhow. Rho to the cyclomatic number of H, product over Ij in H of Wij. What is this number? This is the cyclomatic number. We have already talked about this. An important fact about this number is just that we have Euler relation, which is that V minus K is equal to E minus L. You can never forget it, because you remember that 2 are positive, 2 are negative. V and E are essentially big, and K and L can be potentially small, for example, for a large tree. Tell me. Kg is the number of components in the original graph.
So the original guy is not necessarily connected.
It will be most of times just 1. But writing 1 and Kg is same difficult and homogeneous, so I'll be not sloppy with chalk here. You see, from here to here, you are putting aside some factors of lambda to 0 to 1, something like that. I don't remember, actually, something of this kind. And also I have rescaled W's in order to make Wij and Vij are related this way. I think so. So everything is safe up to when lambda and rho are different from 0 or both equal to 0, things like that. But I like this more because it allows me to study better the cases in which one of the two is 0 and the other is not, which now I discuss in more detail. Never forget that the original q of pods is lambda dot q times q, and lambda and rho are really redundant. This function depends on lambda and rho only through the products lambda times rho up to a trivial prefactor.
Q is lambda times rho.
This is not a rho, also.
That's it.
Yes. And yes, that's all I had to say. I am on the wrong page here. Yes. Now you want to say, well, how do I recognize that? That is just here. If you put w to 1, it's not the multivariate that, but that. And lambda rho are just x is 1 plus lambda, y is 1 plus rho. They are the partition function corresponding to isthmus and to loop. I always interchange them, but I hope that this time I didn't. So you can realize that these have that Grothendieck property, and these are the starting points. So this fixes you. But this is not a historical line, of course. So special cases are one of these two parameters set to 0. If you set to 0 rho, you cannot have loops in your subgraphs, so you must have a forest. If you set to 0 lambda, you cannot disconnect G more than it is already disconnected, so you have maximally connected components. If you set both of them to 0, you cannot do neither of the two things, so you must have a forest in which each tree is invading the corresponding component of G. Essentially, if G is connected, a tree. And the fact is that it is well known that this quantity can be calculated in fast time, in polynomial time, just with a determinant when lambda and rho are both 0. That's the original Kirchhoff theorem, which we are in some sense aiming to generalize. Actually, what happens, and is interesting by its own, is that this partition function is trivial for lambda times rho equal 1, and also computable in polynomial time if lambda times rho equal 2 and G is planar. Because for general G, it leads you to a permanent something like that, a Hafnian something like that, but you can choose signs in the case of a G planar in such a way that it reduces to a Pfaffian, essentially to the square root of the determinant. That's the famous Castellane procedure or Kassenwald procedure and so on, dates back to the 60s. And what happens is that there's not just that I'm doing a list of what I know. This list is almost exhaustive in what you can do. Because besides these cases and other 3 cases of lambda rho being -2, -2, -2, -1, -1, -2, and other complex values, a bunch of other complex values, not that much, the problem of evaluating that function is HP complete. This is a famous result which dates back to some work of the 90s by Dominic Welsh and collaborators, Vertigan, I think, and other people. And I typically call it Welsh plane or Welsh-Jerome plane if I'm also concerned about the possibility of evaluating Z at least in an approximate way. So as everything else is left out of this easy part, in particular, the case lambda equal rho equals 0 and lambda non-zero corresponding to forest is HP complete. We cannot hope that we can generalize our matrix theorem to another determinant, slightly touch the end there, and calculate the partition function in fast time or any other things of this kind, because this would imply HP equal P, which is not quite believable actually. But nonetheless, the matrix T theorem, as we will see, has a kind of Gaussian integral formulation. So it's not impossible to believe that you can generalize a Gaussian integral to a non-Gaussian integral, which calculates formally what you want to calculate, but it is actually HP complete to calculate. Nonetheless, you can do things with it. HP is an issue for worst case, arbitrary bad graph. You can do things which are concrete when you have a serious lattice and you want to do things like understanding the continuum limit, renormalization group issues, and things like that. A non-Gaussian expression can anyhow open you a wide field of applications of tools on the lines of the introduction of the talk of Vincent Rivassol of today. I'm a bit out of topic here. This was going to be said later, but that's not a problem. Now there is something that I wanted to say about the analytic continuation of an model. If you do this question to somebody in my field in statistical mechanics, people will answer, would say, oh, there is a famous PRL by Ninois in 92 in which it does analytic continuation of ON, and it reduces ON to a loop gas. nice, but not totally without consequences. Not nice, beautiful. It's a very good paper and full of consequences, and there has been other more recent papers on the topics in which they do other things. But there are issues which I cannot explain you now, but somehow they motivate the analysis of other possibilities, other tools for understanding analytic continuation in ON. And we will pursue these other tools. They are tools essentially they are called in different names. I can call them dimensional reduction. Well, we want first to generalize this model. We generalize it introducing somehow fermionic degrees of freedom, or in other words, Grassmann variables, which looks like people here do not like so much, but I will have to introduce them anyhow. You have seen them in some flavor already in the David Bridges talk, and he tried to convince me in a private discussion that his way of seeing things is better somehow. Well, he didn't want to convince me. Well, I wanted him to convince me that his way of thinking to the things was better.
But he failed.
And well, he convinced me that it was good in some places that I thought it was bad. But anyhow, I still think that Grassmann variables are a good tool. If you get used to that, you can do many things quickly, and well, you will see that they are a natural generalization of bosons. You have real or complex variables, they are commuting just. You just have that phi I, phi j is equal to phi j, phi I. Well, in general, phi I, anything is equal to anything phi I. They commute with everything. Things like that, we do not call them just C numbers as mathematical do, they call them bosons. Why? Because we introduce things like that, which we call fermions, and instead they do the converse. They take a minus sign. Actually, they commute with all the rest, because all the rest has to commute with them. But you see that in particular, if you generate an algebra over n symbols like this, there is a subalgebra of generated by monomials which are of even degrees, which commutes with everything, because even things, they take double signs everywhere. Actually, what we do is that we introduce a so-called complex Grassmann algebra. Instead of calling fields psi I for I going from 1 to 2n, we use synonymous. We use psi bar I, and now only I goes from 1 to n. We have 2n symbols again, but they are somehow naturally paired. So that now we have even subalgebra, but we also have a stronger subalgebra in which the degree of psi bar and psi is separately equal. This I call it the charge-neutral subalgebra. In the sense, it's like if you are calculating the difference of 2 degrees, which can be thus thought as a charge somehow. And these are anti-commuting all with each other. So we were having here n components, which were bosonic.
So what is the rule of?
Everything anti-commutes. They are just really different names of the same kind of object. You will think that this is Baroque. Why should I have 3 lines here instead of 1? But 3 lines here instead of 1 will save you a lot of effort when you will be writing integrals and things which are huge, and recognize that all the terms you are using are charge neutral in this sense. As they are charge neutral, but you have, for example, say that you have a psi bar I, a psi j, and a function of things which depends on combination like psi bar k, psi k only. You see in a line that you cannot do the proper things here because everything else is paired. But this concept of everything else is paired is easy to see at a glance after that you use a notation which makes paired evident. So,
What is the proper thing?
sorry?
You said you cannot do the proper thing because everything else is paired, or sorry, what cannot you do because everything else is paired?
No, well, if you were just calling this one psi I plus n, well, fine. This is just different names of the same object. The equations are still true. But there are things on your model that you want to see at a glance because they are somehow natural. This is
We'll see later, right?
It's presumably,
Yeah, go ahead.
presumably a symplectic expression.
so. I erase this.
But you have a lot of different blackboards.
Yes, but this is really easy.
So this is, for mathematicians, this is just exterior algebra on n or 2n generators, so far.
And you have seen that also David Bridges with exterior algebra was using this complex notation, isn't it? So it's a justification if you want.
And the 2n is because the underlying vector space has a symplectic expression.
Well, I say that in a moment. I now I want to introduce what I call the OSP and 2M nonlinear sigma model, in which the SP of the name stands for symplectic, and of course the O is the reminiscent for the orthogonal part, which means that I have n bosonic and 2m fermionic degrees of freedom in the sense of the terminology of before per unit vector. I still have a sigma, but instead of being sigma just phi1, phi n, I'll raise it to a multiplet which has these other 2m degrees of freedom, which are anti-commuting variables. So you remember here there was a scalar product, there was a concept of norm. The scalar product was sigma I dot sigma j is equal to sum over alpha a going from 1 to n of phi ai, phi aj. Of course, that's Pythagoras in a sense. But now, with these fermions, we have to do something similar, but you see, you cannot do this very same thing, because otherwise you would have, for example, that fermions do not enter in the norm of a vector, because they will make 0. If you just take the product this way, you have to take something this way. So in a sense, although we were having before just the orthogonal form, now we have a matrix n times n plus 2m, which is squared, in which we have a first part, the bosonic one, which is orthogonal, and a second part, which has block 2 by 2 and is 1 minus 1, 1 minus 1, 1 minus 1, is the symplectic. It's the one that you have to use when you work with anti-commuting variables, in order to make it at least symmetric, for example.
Let me ask a question. So are these variables called anti-commuting because when you pick a state and assign a value to the variables, then the values that you assign to them are anti-commuting?
Well, you should not think that, well, phi could be 2.9 because it's on R.
Yeah.
But psi, it's better you think it as a formal symbol. It never as a number. But it has a concept of integration. You can integrate over the phi in R. For example, e to the minus pi squared over 2 and get the square root of 2 pi, what it is. here you will integrate the psi just as a formal object. And there is a rule that I'm going to tell you because it is crucial to everything. The formal rule is this one. I'm writing too small, sorry. This is the very basis and all of the story in what is called a Grassmann-Berezin integration. Why this all of the story? Why do not I need all the other monomials? All the other monomials are already 0 in the algebra, even before integration. And I cannot do, now I want to do...
You need also the rule integral of 0 is 0. Oh, it's included there.
Well, integral of 0.
Integral is linear.
Actually, the observation of Alan is more than a joke. Integral is linear fixes this rule univocally. You cannot do a different rule without spoiling the linearity of integration. I'm running late on time, of course. And so we have theorems about Grassmann integration, things like, so you have monomials. If you have monomial 0, 1 for each fermion, which means that you have monomial 0, 1 to the n if you have n fermions. So the most general monomial, if you are working here, is product over psi I to ni, but only ni equals 0, 1, say ordered somehow. And what happens here is that this integral, just applying that one after the other, just gives you 1 if ni equals 1 for every I, and 0 otherwise. So you see, this is formal rules. These are formal symbols that you just handle one after the other, anti-commute in order to put it in the proper order, and then integrate. But
We assume the same thing for the barred one.
yes, what I will use every time is this one, which I define this way. And it all the n and n bar must be 1. But you see, this one is better from this one. This one, you are using an ordering 1 to n. If you change it, you take a sign for the permutation. This one, if I interchange this one with this one or this one, nothing changes because this is even. Another time, this is a good feature of the complex Grassmann algebra with respect to the real one that you can use, of course, but it's more painful. And a special application of this one is where instead of having this one, you put here something like a quadratic form. For example, e to the 1/2 psi a psi for an antisymmetric matrix. In this case, you just get the Pfaffian. Just because you single out only the monomials which have the appropriate degree, which is the nth power in the exponential, and you have to rearrange the term in order to saturate them well. And every time you reorder the term, you just produce the signature of the permutation that you need in order to do the proper things. But you see what happens here is that, well, n must be even or something like that, but do not care about that. Although everything seems trivial, you are just playing combinatorially, which is psi, which are marking your graph or your list or your array of points up to when everything is marked fermionically. Everything is marked once and only once. You have all the machinery of integration. Many things here hold. For example, you can do change of variables. Just you have the Jacobian with the different powers. You can do Gaussian integration, things like that. In particular, you can do this Gaussian integral. Compare it with the Gaussian integral that we have used all the time in many of the talks these days. There is a minus sign here. There is no problem with definition of A. It doesn't need to be positive definite. It actually doesn't even need to be. A can be formal symbol, just commuting, isn't it? Well, commuting in the sense of determinant. There is a notion, I will not tell you. And this one, we will use it all the time. In particular, if you put it, for example, psi bar 0, psi 0, you take, instead of that A in which side 0 is being removed both as a row and as a column is the determinant of the minor. OK, I'll go fast. But this expression is our starting point, in a sense. I'm a bit late for the starting point now, but it's a good starting point, however. Because you see that you can matrix T theorem, Kirchhoff, say here, that this one is sum, sorry about that, is the sum over all the trees. Oh, well, in a special case that I will tell you, I change the letter from A to L. This is the sum over trees which are subgraphs of some graph of the product of the edges in the tree of Wij. When does this hold? This holds when Lij is the so-called Laplacian matrix, which is essentially the adjacency matrix changed of sign, but you are putting on a diagonal what you need in order to make it Laplacian. So it's essentially the adjacency matrix. Sorry about that. This is Kirchhoff theorem. With this definition from L, for L, this sum, which is the generating function for the trees, which is exactly this one at lambda equals 0, rho equals 0, is this determinant. It is this integral. I write this here. By my definition, this is that random cluster of GW lambda equals rho equals 0. So in which sense we are trying to gain a generalization of the matrix tree theorem? Well, in the sense that we are putting arbitrary lambda here and see what happens here. If there is an expression here which is still valid, although this will be not valid anymore.
Isn't this also a proof of the matrix tree theorem?
Actually, yes. If you understand the psi bar and psi like marking your graph in this and that way, you can understand from here to here directly without going through here. And this is my favorite proof. But it will be a corollary of my more general way of working. I will work a general lambda, and putting lambda equals 0 at the end, it will be a corollary.
I mean, you just expand it out, and that's what you get, right?
Two ways.
Yes. I actually want to do that in the more general framework in detail. I will comment on the point. This has been one of my motivations for using Grassmann algebra, because when they showed me the two of the proofs, one with Cauchy-Binet on that and one with the marking of fermions, I decided that the marking of fermions was much better, much easier. And so that's why I'm now a fan of Grassmann variables. OK. Now I'll do the claim. So I added a kind of a perturbation linear in lambda, and this is just counting for you the forest with a factor of lambda to the number of components.
One question, if you put lambda equals to 0, then the exponential term disappears? But it
Yes.
It doesn't fall back to this because
You forgot psi bar 0, psi 0.
psi 0 bar?
I don't want to put it here, because this is not doing this one. This is doing lambda to the k of g times this one. But as you see, just doing the derivation, you can update this from here. I'm sorry, this is making confusion, but I didn't find any way in order to avoid this confusion. Okay. And so you maybe want me just to prove this. And this was what Alan told me, not do what you are going to do now. Just prove this. I will do what I'm going to do now. What I'm going to do now is to remember you that I introduced this model. And this model is for some n and m, and the easiest case, non-trivial, not one of the previous one, is to take n equal m equal 1, that is considered OSP 1-2 invariant model, and we gave you all the elements in order to tell you what does this mean. And what I claim is that this one is equal to z OSP 1-2 for a graph G, the same graph G, the same vector of interaction just multiplied by minus 1 over lambda. And I like this much more, because it's not like proving that your favorite statistical mechanics model is equal to something. It's like proving that your favorite statistical mechanics model A is equal to another favorite statistical mechanics model B, which is, I find, more. But this is confusing because there are two equations here, a star and a double star. And so proving two of them is longer than proving one. And this one is not interesting, actually, for somebody who already know how to do that, like many people here. So either you want me to show you both of them, or you decide that I'm running late and I show you only this one. But this is the idea.
You mean the second one is for the whole right-hand side, or only for this e to the lambda something?
No, sorry, it's for the... This expression is this partition function. And the idea for doing this is to recall what does this mean. This was integral over is the sigma, product over 2 delta sigma square minus 1, product over the e to the minus w over lambda, sigma to sigma minus 1. And I told you that I shouldn't do this part of the proof. I'm doing that, actually. But, OK. This is a product over I. So this one, you remember this one was phi squared plus 2 psi bar psi. Actually, I'm cheating here and putting a lambda here. There is a lambda. I put a lambda here from the very beginning, kind of a relative unit between fermionic and bosonic degrees of freedom. Like with where C between time and space, if you want. So this one is equal to 1, which means that phi is equal to plus minus square root of 1 minus 2 lambda psi bar psi. And now you become addicted to Grassmann variables when you understand that this is just plus minus 1 minus lambda psi bar psi. Taylor expansion of things which start 1 plus or constant plus are so easy. You are just truncating the expansion at the degree of nilpotency of what is left, which now is just 2. So this is true. So we are working. If you integrate, here this is kind of the phi, dep psi bar, dep psi. You integrate this out with the delta, and substitute everywhere you were having phi, that means here, with this expression. This one instead of this one. Such a good news for some people doing renormalization and so on, because in this one, for the ON model, the traditional one, you have such a huge number of terms in the expansions. which are bad for the RG properties. Here you do not. Here you just produce the fourth Ferdinand term. And actually, STC squared, you are taking a Jacobian. And the Jacobian is 1 over phi, of course, 2 phi, which is 1 over, well, 2 and 2 simplify. 1 over square root of 1 minus 2 lambda psi bar psi, which is equal to its exponentiation. This is another source in the ON model for an infinite number of terms, and another time this is just a mass term. But you see that these objects, this lambda is appearing here and there everywhere. You cannot tune the parameters. Somehow the fact that the proper model comes without tuning the parameters tells you that the proper model comes because of the original symmetry. I will try to highlight you better on this. The idea is that I rearrange everything here. This is integral over depth psi psi bar. In 4 minutes, I have plenty of time just for doing half of my seminar, but well, so I'll do that this way.
Actually, we started late, 6 minutes.
Okay. So this integral, I rearrange it this way. And then there is a e to the sum over wij, some expression which is this one. That's just the same. I just changed the things and substituted the expression for L. The philosophy is that this piece goes together because it is OSP12 invariant. It's the OSP12 invariant measure. And these things go together because it's the scalar product, which is OSP12 invariant. This goes as so together that I give him a special name, Fij. It is so common to use it that now I generalize this concept to an Fa. Define tau A as this product. You see, the order doesn't matter again because we are complex. Fa is lambda 1 minus cardinality tau A plus sum over I in A tau A minus I minus sum over I different from J in A psi bar psi tau A minus Ij. So it's almost saturated in A. This is saturated, this is almost saturated. It misses 2 fermions either on the same side or on different sides. And everything is charge neutral. This, you see, 1 minus 2 is minus 1. This is exactly what you have here if A has cardinality 2. And I define it because there is a lemma which is crucial to everything. Of course, if A and B are disjoint, Fa times Fb leaving 2 different algebra. You cannot do anything. So if A intersection B is different from 0, you can have something. And the point is that you know everything. Fa times Fb in this case is equal to Fa union B if the intersection has cardinality 1 and 0 if it is larger than 2.
0, not empty.
Sorry, 0 in the information science language. So you see that with these rules, the expansion of this exponential is quite easy to handle. You see you are again, well, this Fij, in particular from this, comes out that it is squared is 0. So I can write this just like, where did I put my erase? There are plenty here. No, okay, here. As I promised it to Alan at the beginning, I was not talking about anything else. So you see there that I can write the exponential as a product of 1 plus wf, and f squared is equal to 0. But so I'm doing the traditional trick. We are summing over subgraphs. Product of the wij for ij in H. And then we have the fermionic integration of this, where there is the measure, which is invariant, of this product over ij fij. But now we have that these fermions, just like the post fermions, just like the Ising spin, they are doing something like understanding topologically H in a different way now. Because now, because of the rules, if you have a cycle in H, you multiply the f along the cycle. When you add the last edge, you have intersection 2, you get 0. So all H which survive at the level of algebraic things here, even before integration, are forest. And the forest, what you get, again because of the lemma, do not depend really on the structure of the forest, but only on the partition of the vertex set induced by the components. Forest differing for the way in which the tree explore the component take the same algebraic structure here. So if you have that F is a collection of trees, and call V alpha the vertex set of T alpha, this is just product of alpha f of V alpha. And so this measure, which is factorized on every side, is such that the integral is factorized on every component. The only way in which I can get here the claimed result, which is lambda to the k of h, provided that rho to the L of h is 0, is that for every tree component, this is producing exactly a lambda. This is the last final check, which is easy because write this as an expansion 1 plus lambda. I call this u is one of the V alpha, for example. And I have here the tau that I described over here, which is lambda 1 minus cardinality of u. Let's call it just v, just not to get, but times tau v plus sum over tau v minus I minus sum over psi bar I psi j tau v minus ij. You see, these terms never contribute to the integral because these are unpaired and everything else is paired. So this one is like it's not there. This one is already saturated. It must use only the ones here. And it gives you just a trivial result, lambda 1 minus cardinality. Then each of these needs two fermions on the same side I and nothing else. So we take the corresponding factor here when at a given I. Well, I should have called this A prime, of course. At the given at I equal I prime, and for the rest only 1. So you get plus lambda sum over I in V of 1. Of course, this is just cardinality of V, and cardinality of V cancel out. Cancel out because this lambda and this lambda is the same, because they were both coming from the original OSP12 model and not from an OSP12 model plus a magnetic field on the bosonic component, for example, which would have split exactly this one. In the original proof, this was understood like a cancellation between the number of vertices here and the number of edges. In a tree, this is just minus the number of edges. Well, now it's easier because it's more algebraic, but somehow the mechanism, the graphical mechanism is hidden in the simple algebra. So I have been quite careful in doing this proof, and I've done nothing else than this, but I'm happy to have done this in detail because I feel like these algebraic tools are useful also per se, and this idea of understanding the proof by exploiting as much as you can the symmetry underlying is fruitful and inspiring, and I could have shown you this better if I could have shown you how it was fruitful in the future, but just trust me.
Okay, I think Andrea, like myself, prepared a 2-hour talk. So you can read his interesting papers for the details. Maybe we have time for 1 or 2 questions, and then we'll have tea.
So usually when you prove something about the top polynomial, you use the deletion contraction recursion.
I never use deletion contraction fruitfully.
So now the question is, does this set OSP satisfy such a deletion contraction recursion? Because then you could use this for proof.
This is true. We use something, we use in OSP directly the reduction of vertices of degree 2 and leaves and so on, but deletion contraction should be there. You're right. I haven't thought about that. This is a good point. Thank you.
Very rough note, if the fermions pick one thing versus another thing, and the thing that's targeted is an edge, it probably is equivalent to deletion and contraction.
Yes, somehow you should succeed in reproducing the deletion contraction procedure on the algebraic level of Grassmann variables. Sorry, there was a...
May I ask, but you cannot do, can you do the whole type polynomial as this Grassmann integral? Can you?
No, I cannot.
Yeah,
That's the exercise for you.
Well, I don't feel like it's a small exercise.
But let me ask you another question. The quantum determinant, can it be written as another non-commutative, let's say integral over other algebra of other non-commutative variables? So quantum determinant, so this Grassmann integral gives you determinant. So can you write Q determinant as an integral?
As much as I know, Q determinants are kind of perturbative deviation from the traditional commuting variables. And are interesting, but I'm not able at the moment to understand them in the full way for using them. Our kind of variables that we use, they are just orthogonal or complementary to traditional commuting variables. They are just exactly anti-commuting, not commuting plus quantum correction. So they are really far away, but Q determinants, I've seen them glancing out of here and there while studying these things, and always being scared of looking at that, but somehow they will be hidden somewhere.
You said something about analytic continuation in N.
Well, I don't do analytic continuation in N, but that's the aim actually. Something which is a smaller aim to prove is that the OSP N2N model, actually, if it has an analytic continuation, this one depends on N and M, not separately, but only on the combination N minus 2M. This would be a kind of analytic continuation statement, a partial analytic continuation statement, which is called Parisi-Surras correspondence. And Alan Sokal can answer better to this question for the status of what we want to do, which is actually what he's going to do.
That's the ultimate goal, is to do the analytic continuation both for the ON and for the ON2M model. Show that they're well defined and ultimately depends only on the quantity N minus 2M. We don't yet have a proof, but we're working on some of the ingredients.
But in which region are you interested? Which region of analysis?
In N and M, in the whole complex plane.
That's why you use those Cayley formulas?
That's right. That one of the main tools are Cayley type identities, which apparently were neither stated nor proven by Cayley. Okay, so let's thank our speaker again.